Imagine you're sitting in the back of an auto rickshaw on your way to school, watching the city roll by. You go home, grab a snack from the refrigerator humming in your kitchen, or turn on the AC to fight off the summer heat. This automation is powered by a hidden computer called an embedded system. These are single-purpose computers. If you sit down at the bulky desktop computer in a school lab, you can open 50 web browser tabs and listen to music at the same time. An embedded system has one job, and it's engineered to do that job invisibly. Because these brains are hidden inside washing machines and microwaves, they have to survive extreme constraints. They must be inexpensive to keep appliances affordable. They run on tiny batteries, sipping microscopic amounts of electricity, and they have to react in real time. If a temperature sensor inside a massive industrial boiler detects that it is about to overheat, the brain controlling the safety valve cannot show a loading hourglass. It must react instantly, within milliseconds. Our physical safety and daily convenience rely on these instantly reacting microscopic brains. If you open up a laptop, you will find a microprocessor. These are powerful, but they require a whole team of separate chips for memory and storage. An embedded system uses a microcontroller, a one-man army that packs the processor, the memory, and all the connection ports onto a single square of silicon. To achieve high speeds on such a tiny footprint, engineers use RISC architecture. Think of a standard computer like a massive, thick cookbook. To bake a cake, the processor spends time reading all the complex underlined steps inside that one command. RISC throws away the cookbook. It only understands very simple, fundamental commands, like crack an egg, stir the bowl, turn on heat. By executing millions of these simple instructions every second, the chip stays efficient. The layout that makes this possible is called the Harvard architecture. Older computers forced both the program instructions and the sensor data to travel down the exact same physical wire. It was like a single-lane dirt road where everything had to wait in line. Harvard architecture gives them separate pathways. By giving data and instructions their own dedicated wires, the chip removes the traffic jam. The processor can read a temperature sensor and fetch its next line of code at the exact same fraction of a millisecond. This physical layout and resource management allow a tiny microcontroller to handle high-stakes, real-time processing. A digital brain only understands binary logic, the absolute concept of on or off. But the physical world outside doesn't operate in neat switches. Light fades in slowly during a sunrise. Temperatures rise in infinite fractions. Physical reality flows continuously, like an ocean wave. If a digital processor tries to read that constantly moving wave, it crashes. So, a specialized circuit freezes the wave for a fraction of a millisecond, converting the flowing physical reality into static, readable blocks of digital data. This translator is the analog to digital converter, or ADC. During that tiny window of frozen time, the ADC measures the exact height of the electrical wave and slices it into thousands of precise digital levels. A tiny change in voltage becomes a specific string of ones and zeros the brain can read. We feed these electrical waves to the ADC using sensors, which act as the physical eyes and skin of the system. When sunlight hits a light sensor, it physically moves electrons around inside the material, changing the voltage that the ADC measures. The machine creates a map of our infinite world by taking thousands of high-speed digital snapshots and putting them together. Once the brain can feel the world, it needs to move it, but there is a power mismatch. A microcontroller operates on just 5 volts. If you wire that weak pin directly to a massive 220-volt water pump, the high-voltage current would flood backward and melt the silicon brain. To solve this, engineers use a relay. Inside, there are 2 separate circuits separated by an empty physical gap. The 5-volt brain sends a signal into a copper coil, generating a magnetic field. That field reaches across the gap and pulls a heavy metal lever shut on the high power side. Because the 2 sides never physically touch, the digital brain is protected from the high-voltage power while still controlling the massive machine. Controlling power also requires reflexes. If an emergency occurs, the brain can't wait until it finishes its current task to stop a motor. We use a hardware interrupt wire, which is like a direct red telephone to the processor. It forces the brain to drop everything and jump straight to the emergency shutdown code. Automation combines these two abilities, safely wielding massive physical power while keeping the reflexes to stop it instantly. Let's look at a smart microwave. Imagine you want hot samosas the second you walk through the front door. We attach a cellular GSM module to the microwave's brain. Now, your smartphone can send a text message with the word "on" to the SIM card inside your appliance. To prevent random spam texts from turning on your microwave, the code performs a security check. It looks at the sender's phone number and compares it against a list of authorized numbers saved permanently in its memory. If the number matches yours, it accepts the command. The brain triggers the relay and the microwave powers up. To ensure the samosas don't burn, we use closed-loop control. The brain continuously compares the data from a temperature sensor against a set point, like 50 degrees Celsius. The processor loops constantly, checking the sensor thousands of times a second. The exact millisecond the target temperature is hit, the logic is satisfied. The microcontroller drops its signal to the relay, the magnetic field collapses, and the power is cut. These smart objects follow a logic loop: remote command, sensory feedback, and instant physical action. We can use these same tools to protect your snacks from a sibling. We start with a capacitive touch sensor hidden behind the refrigerator handle. The human body naturally holds a tiny electrical charge. The touch sensor projects an invisible electrical field through the plastic. When a hand wraps around the handle, it ripples through the field. Your finger acts like a missing part of a circuit, changing the electrical storage capacity of the sensor. If they try to lift your snack box instead, a second sensor called an accelerometer catches them. Inside this chip, a microscopic block of silicone is suspended by delicate springs, monitoring the angle of gravity. The moment the box is lifted, the silicon mass shifts on its springs. That tiny physical shift changes the sensor's electrical storage. This triggers a hardware interrupt, forcing the brain to instantly blast an alarm and send a warning text to your phone. By layering invisible electrical fields and microscopic gravity pendulums, you've built a room that responds to even the smallest movement. Every component we've looked at, the microcontrollers, the sensors, and the relays, is inexpensive and widely available. With a few simple parts and a tool to translate your code into the chip's language, you have everything you need to start engineering. You can build these exact systems tonight at your own desk. The automated future of the physical world is pure logic waiting for you to build it.